this is going to bug us a little bit if you're familiar with digital communications, because digital communications people like to think of maximum likelihood detectors. So they like to think of the maximum likelihood sequence, but we're only going to deal with typical sequences. So for instance, when we deal with channel coding, we're going to deal with a detector that only looks for typical sequences that, given a certain channel input, we're only going to look at typical channel outputs. We're not going to look at the most likely channel output. Okay, so let me quickly say a few words about source codes. Actually, let me just explain what our strategy will be with source coding, and then we'll talk a little bit more about that next time. So source coding. The strategy will be to declare, or excuse me, to encode only elements of the typical set. And if a non-typical sequence occurs, we can do it two ways at this point. We can either declare an error, or we can encode it a different way, with, I want to say arbitrarily large cost. The cost can't be infinite, but we can say with arbitrarily large, but limited cost. So if you're nervous about a source coding scheme that can cause errors, so for instance, you don't want, if you go to your computer and you type zip, and you try to zip something, you don't want errors to possibly occur. If you're nervous about that, then you can just say, okay, if it's atypical, I'm going to encode it some different way, and it can cost as much as, like, in other words, the length of the encoded sequence can be as much as I want, just as long as it's limited. So on average, what's going to happen? So if I only encode in the typical set, the cardinality of the typical set is approximately equal to 2 to the 8 and 8 of x. In particular, let's think of bit-to-bit mappings. So in other words, the random variable x the random variable x can take two values, 0 and 1, and I'm mapping it. When I encode this, the bits are implicit because we've been taking all the bases as log 2. So I encode, this is x is in 0 to 1, 0, 1, so therefore the length n sequences are in 0, 1, n, so that means n, length n binary vectors, and we'll encode them as binary vectors. So, we start with n bits. And we're only going to encode elements of the typical set. So what we're going to do is list all binary vectors in the typical set in any order. And at the top of the list, basically will assign them each a n h of x bit representation. So in other words, we'll have a list like this. Here are the sequences in the typical set. And so on. So these will be sequences in the typical set, listed in any order. And on this side, we'll assign the first one, well, 0, next one, 1, 1, 0, and so on. So basically it's a mapping from elements of the typical set to binary sequences. Since this list has 2 to the nh of x elements in it, I should be able to assign each one a unique index of size nh of x. So the average length will be the probability of being in the typical set, and each of those elements of the typical set gets a sequence of nh of x, plus if it's outside of the typical set. So let's take the second approach. If something outside of the typical set occurs, I'm going to assign this an arbitrarily large cost, c. I don't really care what c is, but as long as it's less than infinity. What is this? Probability of being in the typical set. That's approximately equal to 1 minus epsilon. Which means that the probability of being outside of the typical set is epsilon times this cost. So therefore, using this kind of an encoding scheme and picking epsilon as small as possible, I can achieve a source coding with, on average length, nh of x, regardless of what c is, because I can make epsilon as small as possible. So this is a mathematically feasible, but computationally highly infeasible source code. The number of sequences here is 2 to the nh of x. So if n is like 10,000 or something, and h of x, let's say, is 0.5, then the number of sequences in this list would be 2 to the 5,000, which is around 10 to the power of, it's more than 10 to the 1,000, which is something like 1 billion times more than the number of particles in the universe. So this technique, basically what this is telling you is that mathematically this is possible, but computationally it's totally infeasible. So what we're going to start talking about next time is how to design computationally feasible source code. So there's some clever techniques you can use. We're going to talk about the Huffman procedure. And later on we're going to, if we have time, we'll talk about actual practical encoding schemes that are used, such as zip. Okay, any questions on anything we talked about today?
Is L the length function?
Yeah, so remember in our first class,
class,
yeah, we talked about the average length. That's what I mean by that there.